This is John Black, Super Chemist. First thing we're going to talk about is silica gel. Now this, keep in mind, is not my strong area. I don't know really anything about silica gel more than the average person does. Well, most people know of silica gel is that they have little packets, and inside the packets are these little beads, and they put them into tools, maybe to keep the water out. Everyone knows because they put them in clothes at the store. If you buy clothes at the store, they'll have them in the pockets and stuff. If you have weapons, bullets, you might put it into that case so that it dries it out. And I think everyone knows what they are, at least that much. But you can also make silica gel, but it doesn't look like those beads. That's what I don't understand is, what are those beads? How are those beads made? Because when you make silica gel, it's kind of more like sand, you know what I mean? It is sand, as a matter of fact. But it's a porous form of amorphous silica. It's a free-flowing powder. That's why I don't understand what those silica gel beads are. How are they beads like that? Anyways, it's free-flowing powder that is 99 plus, meaning more than 99% silicon dioxide. So it's basically just silicon rust that has pores in it. Down here, I want you to look at this thing. This is a molecular sieve. If you see it up close, it looks all round, and you don't really see these indentions and stuff. But the way a molecular sieve, like I bought 3A molecular sleeves. That means the holes are 3 angstroms wide. An angstrom is, I think an angstrom is 100 picometers. 10 angstroms is 1 nanometer, I think. Anyways, it's real small. So that means that the pore size from here to here, right, is 3 angstroms. And water is about 3 angstroms, right? See how big oxygen, O2? That O2 ain't going to fit in there. You know what I mean? N2, nitrogen isn't going to fit in there. Carbon dioxide isn't going to fit in there. But look how H2O, water, fits nice and snug in there. The thing is since no air can get in there, this is a vacuum. Okay? And when the water goes in, it can't come back out because there's a vacuum behind it. When it goes in, if you try to pull it out, you're pulling on a vacuum, and you can't get it out without heating it up or whatever, or putting it under a vacuum. Now that's how a molecular sieve works, okay? And that's what I used to think silica gel did. It had the pore sizes, but they weren't all 3 angstroms, but some of them were, and they collected up water. That's what I thought. I don't think that's the case, because as you see right here, pore size average for beads, the stuff that they put in, in the little packets, on average are about 25 angstroms. That's a lot bigger than 3, So anyways, pore volume is, I just have a couple little facts. Pore volume is 0.6 to 1.2 cubic centimeters per gram. Surface area is from 300 to 750 square meters per gram. And the beads are about 800 square meters per gram. Mesh sizes. These are the different types of mesh sizes: 3 to 8, 6 to 16, 40 to 20, and so on. And so they go all the way down to 325. This is the opposite for the size of the grain, because the smaller the mesh size number, the bigger the grain size will be. Okay, so if you want it real powdery, you'd go down lower. If you want it to be more granular, less powder, you'd go back up to the low numbers. You know what I mean? You want powder, high numbers. And you can think of it as, let's say you had a round circle, and you put it in between two, in a pipe, right? And then you dumped your stuff in it. If you have 2 holes, right, the holes are going to be that giant, right? So you'll have giant things go through it, right? But if you have, say, 14 to 42 holes, right, the holes have to be a lot smaller, right, to get them in there. So that means the grains that you would pour into the pipe and like sift it through, like, are going to be smaller. And just think, if you put 325 holes on this, the holes are going to be like so tiny. I mean, it's going to be like a powder when it comes through. That's why the smaller the number, the bigger the grain size. The bigger the mesh size number, the smaller the grain size. All right. Now, what pore size do you want for this to make sodium silica gel? Well, you want 50 to 1,000 angstroms pore size, right, from here to here. That would be okay, right? Better would be 100 to 300 angstroms. And the best, what you really, really want, is 150 angstroms. If you can get it all to be 150 angstroms, that's the best deal, right? Mesh size. The mesh size you want is 30 to 60. That's the best. Have no water indicators. You know, sometimes silica gel has indicators in there, and when it soaks up the water, it'll turn blue or it'll turn pink or whatever. Don't get that. You want it white. You want it, you don't want no contamination in there. If you want to buy from a chemical supply company, I don't know these companies, so don't think I'm saying they're good or whatever. I have no clue who they are or whatever. I mean, I've heard of Aldridge. You might have to be a chemist to buy there. I don't know. This is just something I read, and I figured I'd put it down just in case someone wanted to whatever. Zeolites. Zeolites is a aluminum silicate, okay? And they have someone, I don't know anything about it. I just read one sentence that said basically what I'm telling you now. They use ZSM-5, absorbs up to 12% mole, by mole in metal, but apparently that's not good enough. 12% is too low to make the reaction go good, and you want like 30%, and I'll get into that later. But you might be able to get some kind of zeolites. I don't know how they sell those or how they whatever. But if you can get them, that's 150 angstroms, 30-60 mesh, they might work. But I don't really know anything about these to know, what I know Z probably stands for zeolite, but SM-5, I have no clue what that means. So anyways, there's some places you can order from, and I'm sure you can buy some stuff on eBay or whatever, you know what I mean? And you can see, remember, the average pore size for beads are 25 angstroms, and you need 50 to 1,000. So the beads, I don't think, would be a good idea. Now, when you get your, let's say you got some 150 angstroms, you got some 30-60 mesh, it's silica gel, no indicator, no water indicator, it's nice and white, free-flowing powder that you have, right? Now that is more than 99% silicon dioxide, okay? But it does have, because it soaks stuff up, right? It soaks stuff up into the crystalline lattice. The holes in the crystalline lattice are like, I guess, the perfect size for water. I'm just guessing. And the water gets sucked in there along with air, though, too, I guess. So I don't know what the deal is. But I know it gets sucked up in there from the crevices in the crystalline lattice. And you'll have gases in there, water, air, that kind of thing. You want to get rid of that stuff first. Obviously, you want to definitely get rid of the water. Sodium and water ain't a good thing. How do you do that? Same way you do with molecular sieves. You put a vacuum on it, right? You heat it with a hot hair dryer. Then you heat it with, you do this slowly. You don't just, heat it you're doing your thingy, pull away. You know what I mean? And heat it a little bit more, with your heat gun, pull away. Heat it with your heat gun, pull away. Heat it, you know what I mean? Until you get it up to as high as I can get it, and then use a torch. The same with the torch. You don't put a torch on there and just torch it, man. Put your torch on, move it around the whole time, around the whole, and take it away. Put it, you don't want it to go too fast. You want it to get about, and that should get it up to at least 300 C. That's what you want to get it up to. Um, and let it, everything, all the water gets sucked out by the vacuum and the heat. It's going to be forced out, and you'll have nice, clean silica gel, right? Now, I don't suggest this, although you could do it. And the only reason why I don't suggest it is because if silicon dioxide is 99 plus, meaning more than 99% silicon dioxide, then there's so little of this SiOH that it doesn't really matter to me. I mean, but if you want to do it the perfect way, and keep in mind, this makes siloxane, so I don't know if that doesn't sound good to breathe. But you basically calcinate it. Take it up to 600 degrees, and what it is the impurity in the crystalline lattice is silicon hydroxide, I guess that would be. And if you heat it up to 600 degrees, you'll make this siloxane, where you got the silicon disilicon oxide. And that will just basically evaporate away. But you don't want to breathe that, that's for sure. You know what I mean? So you better have a fume hood or something. And then after you calcinate it, you know what I mean? You heat it up to 600, make sure, for a while, get rid of all that SiOH contamination. Now you have 100% SiO2, silicon dioxide, no water in it, no contamination. It's 100%. Let it all cool down to room temperature. Like I said, this step is not required. You know what I mean? The sodium metal will react with the SiOH, or the silicon hydroxide, or whatever that's called. But I mean, how much is there? If there's a 0.5% of it is that, I mean, I don't know. I guess it would be up to the individual to think about that. I did want to talk about the beads again here. Type A, B, and C, right? There's 3 main types. First type is about 25 angstroms. It's used for, that's the pore size. And it's used for drying, like I said, in the little bags that you have in clothes, or weapons, or whatever you want to dry out. Acts as a desiccant, mainly that's what it's used for. Then you have type B. It's 45 to 70 angstroms. Well, that's actually getting better, and that's used more to absorb liquid stuff like perfumes, things other than water. And also it's used in some kitty litters. Then there's a type C, and it's mainly used for kitty litter, okay? And all it says is micropored, so I don't know how many angstroms it has, but type A has 25, type B has 45 to 70. Maybe this one's even bigger in pore size. Maybe it would be 100 to 200. And that would be perfect, but you need 150. 100 to 300 would be better. 100 to 200, that'd be better than 100 to 300, you know what I mean? Now the next video I'm going to get into how to make the sodium silica gel, which is easy, actually. Stage 1 is the best for pretty much all the reactions, because you can use this stuff not only for the Boulevard blank reduction of esters, but you can use it like for the Wurtz-Fittig coupling, a bunch of other reactions